different trig integrals. So let's look at a bunch of different trig integrals here. First up, let's look at this one. We've got sine cubed cosine to the fifth. So on this one, what we could do is pull out one of those sines, and we get sine squared cosine to the fifth times sine x dx. And then we'll rewrite the sine squared as 1 minus cosine squared. Let u equal cosine x, and du is going to be minus sine x dx. And so we can rewrite it like this. Distribute that 5 across. Distribute that negative into there. And that gives us this for our answer, and putting it back in terms of cosine gives us this. All right, now we could do this one as well using, instead of using u equal cosine, we could let u equal sine. And so we'll save one of those cosines out there to be part of our du. If we do that, then the cosine to the fourth becomes written as cosine squared, quantity squared. And we'll replace that cosine squared with 1 minus sine squared. And now we can distribute, or well, we'll go ahead and replace each of the signs with the u. Then we'll have to square out the 1 minus u squared. Then distribute the u cubed across that. That gives us this integral, which we can do easily. And then replace the u's with sines to get that. Now, this integral, we did it two different ways, and we got two different looking answers. We got that and that. If we graph both of these things, we can see that they differ by a constant. Now, here's a question. Can we show algebraically that they are the same? The answer is yes, but it's a long and ugly process. I'm not going to ask you to do this, but if you just want to see it being done, if we start with this one, we can rewrite each of those cosine to the 8 and cosine to the 6th. We can write those as cosine squared to the 4th and 3rd power. Then we can replace that cosine squared with 1 minus sine squared. Then raise those to the 4th and 3rd power. So let's see, for simplicity, we're going to write z for sine squared. Now if we raise that to the 4th and 3rd power, that gives us this. We can combine that together and get all this stuff. And we can rewrite it like this. And remember, z was sine. So we can rewrite it like this. And we get the expression that we had involving sine, but it's got that minus 1/24 on the front because they differed by a constant. Okay, let's look at this example. Sine squared times cosine squared. In this case, we have to replace both of these with using the double angle formulas. So that gives us this. So we'll bring the two halves out front and multiply them together to get 1/4. Then we have to multiply these two things together. Foiling it out gives us this. Now the cosine squared, we have to use the double angle formula again. So cosine squared of 2x is going to be 1/2 times 1 plus cosine of 4x. So we'll replace that in the integral, and it gives us this. Now I'll distribute that half through there and combine the minus 1/2 with the 1. That gives us this. And now we can integrate easily. Or well, I guess first, before we do that, let's factor out the half. Now we can integrate that and get this. And that's our answer. Or that's our answer. Okay, what about this guy? We got cosine squared over 1 plus sine. So if we use our Pythagorean identity, we can do this with no substitution. Because cosine squared is 1 minus sine squared. And that's a difference of two squares. So it can be factored into 1 minus sine x times 1 plus sine x. Then we can cancel those 1 plus sine x's, and we're left with this. And you can integrate that to get x plus cosine x plus c. And we're done. Okay, what about this guy? Tan cubed over cosine. Well, this one, if we let tan be sine over cosine, we can rewrite it like this, which gives us this. And now, it's more like the problems we've been dealing with. We can pull one of those signs out front, since the power of sine is odd and it's on top. We can pull it out, I guess, out back, and then let u equal cosine. We'll replace that sine squared on top with 1 minus cosine squared. Let u equal cosine. And then u substitution will finish this off. Notice in the end there we've got 1 over u, and when we replace the u with cosine, 1 over cosine gives us secant. All right, tan to the fourth. I think we already did this one in the other video, so we'll just do it quickly. Rewrite it as tan squared times tan squared. Or rewrite one of those things as secant squared minus 1. Distribute the tan through there. Then we get this, and tan squared secant squared minus, let's see what's going on there. In this step, we've got secant squared x. That integrates to give us tangent, and the minus 1 integrates to give us, I think that should be minus x there instead of plus x. But the tan squared secant squared, we can do that by letting u equal tan x du secant squared, and we get this. And again, I think I made a sign error here. That minus 1. Actually, no, it's not a sign error. The negatives go together and make that plus x. So that's correct. All right, that's the end.